Hello everyone, my name is Changgang Zheng. Today, I'm presenting our work on rapid prototyping of in-network machine learning inference. And let's start with, what is in-network machine learning? In-network machine learning refers to the offloading of machine learning inference tasks to programmable network devices. It is a type of resource-constrained machine learning that runs within the data plane of programmable network devices. Unlike other resource-constrained machine learning, you can't just compile the code to run on a network device, as the pipeline architecture is too different from a CPU or a GPU. Still, one may wonder, why bother using in-network machine learning given all the existing solutions? The motivation is what we call the 3 L's. The first L is location. There are always network devices on the path from a data source to the cloud. In-flight processing therefore makes sense. Furthermore, network devices aggregate data from multiple sources, allowing better observability than on an end device. And the best is that these devices are already part of the infrastructure and don't require extra power or space. The second L is latency. Terminating data on a network device along the path to the cloud will always have lower latency than processing in the cloud. Therefore, in-network machine learning can significantly reduce latency. The last L is for load. Network switches can process and classify billions of transactions per second. Transactions that no longer go to servers, therefore reducing the load. The last 5 years have seen quite a lot of works on in-network machine learning, but these works mainly focused on mapping a single model to a single device for a single application. To make in-network machine learning practical, a rapid prototyping solution is required. The solution needs to support easy configuration and modification of deployed models, and easy migration among platforms and use cases. To explain this point, we studied the lines of code that require change if you change a single parameter in a deployed model. This number can reach hundreds of lines in the data plane, for example, if you use random forest, and also tens to hundreds of lines in the control plane. Such a manual modification is both time-consuming and prone to errors. But rapid prototyping is not enough. There also needs to be a general way to map a large number of machine learning algorithms to the data plane, and doing so efficiently, so the models would fit within an unmodified, off-the-shelf hardware targets. To achieve these two goals, we introduce Planter. Planter takes a use case from the training dataset all the way to a deployment on a target with a single click. So given a dataset, Planter trains a model using a framework such as TensorFlow or scikit-learn, and its front end enables auto-tuning. The trained model is mapped to P4-based data plane code and control plane code, typically in Python and P4 runtime, including match action table entries. Planter also auto-generates bash scripts and code for testing. After that, Planter compiles the generated code, loads the model to the target, and tests it. And ideally, in-network machine learning should run on a range of programmable network platforms, from high-end switch ASICs through smart NICs and FPGAs to cheap low-end devices such as Raspberry Pi. Planter supports in-network machine learning across all these targets with easy migration between platforms. To realize machine learning mapping, we define 3 general methodologies. The first one, direct mapping, is suitable for sequential algorithms, where the workflow matches the pizza architecture. For example, a decision tree, where each logical stage is a split in the tree. The second methodology, encode-based, slices the feature space and assigns the code for each slice. This constructed code allows to achieve a decision at the end of the pipeline, and it matches both tree-based models and, for example, k-means. This methodology enables high table parallelization, thereby enabling good scalability. The last methodology, lookup-based, looks up the results of computations within match-action tables, using some smart transformations, and is suitable for algorithms such as SVM and knife Bayes. Overall, these methodologies allow Planter to support more than a dozen models with 50+ different variations. Planter is a modular framework that separates machine learning models, P4 architectures, targets, and use cases. This means that the user can pick the right model, the right target, and the right use case. And Planter takes all these parts and turns them into a single program. Because Planter is modular, it is easy to extend it with new modules, use cases, and targets. The P4 code generated by Planter has 3 components. First, architecture-related components, in purple, create the program skeleton. Second, use case-specific code, in amber, is added. And last, machine learning model-related code, in red, completes the program, embedding it with training results and user configurations. Planter achieves high machine learning performance that for most models is similar to running the same size model on a server. For example, this slide shows the FN score for an anomaly detection use case using the UNSW dataset. As you can see, the switch-based models in blue are on par with server model in amber. We also compare Planter with several state-of-the-art solutions. Planter achieves higher F1 score than Clustream, Torus, and Homunculus, and for similar models, requires significantly less memory than Easy, while in all cases fitting on an unmodified Tofino switch. We provide further comparisons in our paper. Planter achieves high machine learning performance without compromising system performance. The figure on the left shows the throughput on various Planter-supported targets, achieving full line rate on Tofino and 100 gig on Elvo U280 FPGA. The figure on the right shows the latency overhead of Planter, meaning the latency on top of normal forwarding. You can see that this overhead is in the order of nanoseconds to tens of nanoseconds on hardware targets, and less than a millisecond on software targets. Planter has already been extended to support different deployment scenarios. In a hybrid deployment, a small in-network machine learning model is deployed on a switch, and the large machine learning model at the backend. Only high-confidence decisions are made inside the network, and others are sent to the backend. In this manner, the same accuracy is achieved as a very large machine learning model, while also reducing server load by about 70%. In a distributed deployment, we disaggregate a large in-network machine learning model into small components and distribute them across multiple programmable network devices, allowing to further scale in-network machine learning models. Last, federated learning is enabled. for privacy-preserving scenarios, with Planter-generated models deployed in multiple places. Moreover, as there is data skew over time, runtime model updates are supported and hitless. Planter's early adopters have used it across a range of use cases. For example, network functions include load balancing using Q-learning and IoT traffic classification. Cybersecurity applications include e-commerce bot traffic detection and smart grid false data injection detection. Finance-related applications include predicting future stock price movement and transaction fraud detection. And be sure that there are also many more applications to explore. In summary, machine learning inference can be efficiently mapped to programmable network devices, achieving high machine learning performance with low resource overheads, fitting on different commodity network platforms. Also, there are many new applications to explore using in-network machine learning, and Planter enables you to easily develop and deploy your own solutions by extending the current framework. So, in the end, we invite you to try Planter today and change the future of networking.